let's look at the idea of periodic trends. Now, elements in the periodic table show trends in their physical and chemical properties across periods and both down a group. Now, this is by far how a true periodic table looks like. It's actually including the F block in between the S and the D block also. So we saw some of the S and the D blocks earlier, and S blocks are the elements in groups 1 and 2. D block was the old transition elements, and P block was groups 3 to 8 or 13 to 18 now. The ones that are colored light blue here are all your metals. So you can divide your periodic table in terms of metals and non-metals, in terms of groups and blocks and periods and all that stuff. So earlier you had groups 1 to 8, but now recently the IUPAC has recommended that the periodic table be divided into groups 1 to 18 and ignoring the F block. And generally speaking, if you remember, the F block was written separately. So groups 1 and 2 were labeled now 1 and 2, but the transition metals are now labeled from 3 to 12, and group 3 is now 13, 4, 14 all the way to 18. And that's a big change now. All right, that's the first change. And the second thing, and the reason why the properties, and we're going to be talking about more about the chemical properties and electronic configuration, are because chemical properties, or even predicting the trends in chemical reactions, is determined by the number of outermost electrons. So electronic structure is actually what determines the chemical properties of an atom. Not just that, it also determines the properties of individual particles like atoms or ions, their sizes, their ionization energies, their properties like in bonding, their polarity, electronegativity, ion size, cation size, anion size. All of those things are determined by literally the electronic configuration. And something else about forces of attraction we'll talk about in just a few minutes. But first, let's just recap what we have learned about the periodic table. So in addition to this, the fact that there are groups 1 to 18, and most periodic tables don't have this F block because we never are going to bother ourselves with this F block, is we also know about the staircase. The staircase kind of divides the metals and the non-metals. Here is a shorter version removing the F block, which was here, to only have groups 1 and 2, where hydrogen is forcefully put in group 1 because it's an X block element, but it doesn't behave anything like group 1. And then you got the whole staircase. So all of these are metals. These purple ones are your non-metals, and these blue ones are your noble gases, and they're called group 18, and this is called group 17. So you got the S block, you got the D block, you got the P block. And by technical definition, what are S block elements? S block elements are those elements where the electron or the highest energy electron occupies an S orbital. What's called the P block, where the highest energy electron is in the P orbital, and the D block is where the last electron went into the D orbital. That's one of the things. We can also, by the way, divide group 1 into other categories that we know that this is better known as alkali metals. Group 2 is known as alkaline earths. We have more detailed names because there are more ways to divide the periodic table. One classification, like I said, was S, D, and P blocks. Then earlier in O levels, you definitely have done the whole metal and non-metal thing. That's the second way of classifying elements in the periodic table. This would be a way to classify elements into metals, D block, which is your non-transition elements, and still metals, and the staircase is the metalloids, and a small list of non-metals, reactive non-metals, and unreactive non-metals, which are your noble gases. That's another way of classifying elements in the periodic table. So if I combine the idea of metals and non-metals and the groups, we actually even have some names for certain groups. Like the most reactive metals are those found in the first group in the S orbital, meaning the S blocks. So now the S block elements are actually both reactive, but even group 1 is more reactive than group 2. Group 1 is called alkali metals because literally they make alkalis in water. Group 2 is called alkaline earth metals. They're a little less reactive than alkali metals. D block are generally called transition metals. They remain metals. They have a lot of metallic properties. Then you got the staircase. You got some metals here also, which is unreactive metals. Then you got non-metals, and the most reactive non-metal group is the halogen, because it's all the way down, it's actually just non-metals. That is group 17. We study groups 2 and group 17 in much more detail in A levels. The last one, group 18, is your noble gases. So this is another way of dividing your periodic table. Now, why are we dividing a periodic table? Because we're going to talk about periodicity of atomic properties. There are properties that we're going to study, but we won't study this whole large periodic table. We look at a much simpler periodic table. So we're going to look at a much simpler periodic table, the one that involves the first 20 elements, because we are really going to be talking about the periodicity in simple periods like period 2 and period 3. Period 1 has just 2 elements, doesn't matter. Period 4 starts getting transition elements, whose chemistry we will study in second year chemistry. In the first year chemistry, we are going to look at some properties that vary across period 2, period 3, or even down groups. Properties include things like atomic structure, atomic radius, ionization energy, electronegativity, reactivity, ion size, atom size. We're going to look all of that. Now, obviously, it is all based on the configurations. The reason why we even have periodicity is literally because their configurations match. So we are going to focus on period 2 and 3 and look at their configuration. Period 2 and 3, the elements in group 1 end in S1, they end in S2, SP1, P2, P3, P4, P5, P6, and then the properties repeat again from period 3. So yes, so that's what we have. We are going to look at this. The syllabus explicitly tells us to study the properties of period 3, which is sodium to argon. But please appreciate that whatever the trend of properties are in period 3 are also the trend in properties in period 2.
Quick pause. If you're finding value in this explanation, there's so much more to discover at Alt Academy, where we break down every A-level concept with the same clarity. Now back to the video lesson.
All right. So that's what we are there. Now, why am I talking about this? Why am I talking about this? We are talking about this because there are certain, like I was mentioning, the properties. What properties I was mentioning? Well, to study the periodic chemical properties of elements, we should study the atomic properties. So things like atomic size, things like ionization energies, things like ion size, things like electronegativity. Yeah, that idea. Things like forces in bonding, even intermolecular forces, forces of bonding, even intermolecular forces, even the structure. All of this can only be studied if we had studied electronic structure, which is what we just finished. Hence, this is the best chapter to start with. Now, but to study all of this, so we need electronic structure, and we also need an understanding of a law in physics that you will do in second year physics. But it helps to talk about it right now. It is called the Coulomb's law. Have you ever heard of Coulomb's law? Coulomb's law. Now, what is Coulomb's law? Coulomb's law is literally about helping us understand it is about charged bodies, but it also helps us understand how the atoms and the forces inside atoms are going to be talked about. Well, in an atom, we have a proton, we have a nucleus, we have electrons around it, right? So there is always an attraction between opposite charges, and we've got, repulsion between electrons. We all know that, yes? So we've got to talk about this force. So this force of attraction between oppositely charged bodies, or the force of repulsion between like charged bodies, is literally proportional to the quantity of charges on each of the two bodies multiplied, and inversely proportional to the square of the resistance. It is directly proportional to the multiple of the charges. So meaning what you need to know and understand in chemistry is, if you are talking about the force of attraction, an electron feels from a nucleus, and if the nucleus's charge increases, that force of attraction will increase. If the electron moves further away, If it goes twice as much away, then the force becomes 1/4 because twice squared. So distance becomes a big important factor in affecting the force of attraction and repulsion. And similarly, charges, their repulsion and attraction. So for example, two electrons repelling each other will have less force than a nucleus pulling an electron, because the nucleus will have 10 plus, 20 plus charge, or 15 plus, but an electron only has 1 minus charge. So electron to electron repulsion is less, but the nucleus to electron attraction is more. Yeah, so these are the things that we are going to do. Basically, if you take this and you simplify it, first of all, opposite charges attract and like charges repel. The bigger the charge, the greater the attraction. The further the distance, or the further apart the particles, the lower or the weaker the force. So like I was saying, this Coulomb's law simplifies to this. You don't have to know this. You will study this in physics next year, yes? This will be part of electric fields in physics next year, yes? But simply saying that in chemistry, the physics of the atom is so important to understand. The physics of the atoms is that opposite charges will attract, meaning a proton and a neutron electron will attract, but like will repel. The bigger the charge, the stronger the force. And where do we see bigger charge? We see them in nuclear charge, yes? And the further apart the particles, the weaker the force of attraction. All of this together will help us understand what the hell is going on inside an atom. That's the crux of it, okay? This is the whole game we got to play. What kind of forces are we talking about in an atom? Let me show you. So in any atom, there is attraction between the nucleus and any electron, but there is also repulsion between electrons. And so the sizes of an atom, how strongly it is being attracted, all depends on the size of the attraction and size of the repulsion. And the net attraction is what determines how large or how small it is, how strongly it is held, how much more can it be lost easily or gained, or it is shared evenly or unevenly. All of that stuff depends on this kind of attraction. All right. So yes. So in the next few things we'll be seeing is ionization energies, atomic size, ionic size, electronegativity. All of those things are just dependent on these forces of attraction and repulsion. All right. So if Q1 and Q2 is applied here, or Coulomb's law was applied here, Q1 would be the charge of the nucleus, Q2 would be the charge of the electron, and R squared would be the distance between here. So mathematically, this is how you would calculate the force of attraction. Obviously, we'll need to know proportionality constant, but who cares about the actual value? In chemistry, we're just going to talk about the trends in value. So relationship matters more. So if this was a 10 plus nucleus and versus a 20 plus nucleus, a 20 plus nucleus will attract it twice as much than a 10 plus nucleus. So Q1, Q2 for this force of attraction is the charge of this and the charge of this, meaning 10 plus into 1 minus. But repulsion ke liye, for now, it will be the charge of this and the charge of this. So repulsion will be weaker and the attraction will be greater in the Coulomb's law. All right? Yeah. Now, if you're still stuck on the formula, remember, the formula is not to be really used mathematically for chemistry. It's there for you to understand that, look, it makes a difference if you understand the physics behind the atom. And the idea is that the force of attraction between two charged bodies or the force of repulsion between two charged bodies is directly proportional to the quantity of charge and their distance. So if I'm talking about, let's say, sodium's 11 plus nucleus, and I somehow want to talk about what the outermost electron in the 3s1 is experiencing, that force of attraction, literally the force of attraction would be directly proportional to 11 times 1, which is 11 is the charge of the nucleus, and 1 relative charge of the, we're not using actual charge. We should have by using Coulombs, but we don't know the charge, and we can't really bother about using it. But it'll be 11 times 1 over the distance. Now what's the distance between the third shell and the nucleus? Squared. Now if this is the force that represents the attraction that the outermost electron in sodium feels, just to talk about it for magnesium, you know magnesium is in the same group, right? Same period. So its electron is 3s2, the outermost electron, the third shell. So you would say it's the third shell is the same distance away for both of these guys. But the force of attraction that magnesium's electron feels is going to be greater than the force of attraction between the nucleus and the outermost sodium's electron. Why? Because if I talk about that outermost electron, bhale wo 3s2 is 3s2, but it's for each individual electron, that force of attraction, that each individual electron being pulled by the nucleus will be pulled by a 12 times force. So the force on magnesium's outermost electron will be 12 times 1 over r square. And imagining the distance is the same, whose force of attraction will be greater? Magnesium's will be about maybe 10% more or 9% more, because 12 times 1 is 12, 11 times 1 is 11. So magnesium's is greater force of attraction. And basically the idea being that use that idea not exactly mathematically, but just basically, just relatively. So we'll be talking about the force of attraction between things like sodium and magnesium, and you'd have to just figure out whose attraction will be greater. The force in sodium will be greater, or will the force in magnesium will be greater? Knowing that magnesium nucleus has a greater charge, it will have a greater force. Yes, we'll also talk about shielding effect, which will be the repulsion between electrons, and they're also governed by the same law here, and that's coming up. And Q is the quantity of charge here. I assume that was understood, but now I have to spell it out. Q is the quantity of charge and R is the distance between the charged bodies. Hey there. If you found this A-level chemistry lesson helpful, why don't you head over to our website, altacademy.org, where you can sign up for the full A-level chemistry course. In addition to chemistry, you can sign up for physics, biology, math, or 4 other A-level subjects. Thousands of students have already taken the leap. What are you waiting for?